All right, hello and welcome to our review session 2. This is our first virtual review session. And as promised, there will be a variety of very cute Cali photos embedded throughout this presentation as your incentive to make it all the way through. There are quite a bit of slides, lots of different content to cover, and I'm going to go through it pretty quickly. So if you need it at a slower pace, just go back and rewatch or slow down the video on YouTube, and you'll be able to get through it that way. So to start us off, here's Callie K. Cassette, a day after she was born. All right, our topic today is everything related to motion and forces. In most physics classes, this is most of the course. For us, this was 1/4 of our year. So we fit a lot of stuff into the very beginning of our year that I want to remind you about. First of all, these are our very important kinematic equations. They are provided to you in your data booklet. Remember that each one uses different sets of these SUVAT variables. And depending on which variables you have and are looking for, that dictates which one of these equations you ultimately want to use. Before we talk about the motion part of this unit, I want to review this idea of finding components of a vector. Remember, most of the time we are given a vector that is not at an angle or not at one horizontal or vertical set. So we can break this down into components where we have a horizontal and a vertical component to this vector. Our data booklet gives us an equation for it, or you can just remember how triangles work. But the horizontal component of this, as the data booklet states it, is A horizontal, AH, is equal to A times the cosine of theta. Basically, if we want to find this orange arrow, just take the cosine times the hypotenuse, and you end up with 20 times the cosine of 34, which will give you 16.58 newtons. Do the same thing for the vertical component. AV is equal to A times the sine of theta. Again, this is found in your data booklet. That is equivalent to 20 times the sine of 34. Make sure that you're in degree mode for all of this, actually the entire test, and you'll get 11.18 newtons. We will be coming back to that in just a little bit. So going back to these kinematic equations, if you have a problem like this where it's just talking about free fall again is an object's motion when there is no air resistance. Ask how fast must you launch the baseball straight in the air to reach the height of the Empire State Building, 380 meters, assuming no air resistance. There are some things that we know about this scenario. We know that 380 meters is equivalent to S, that's our displacement, 380 meters. And since we are going up, we're going to keep that to be a positive displacement. We also know that at the very highest point of this trajectory, our velocity is 0. So it helps us to think about this as an initial and a final, that we're just talking about going up. So our final velocity, v, is 0 meters per second. And then the last variable that we know is we know acceleration for free fall is always a negative 9.81 meters per second squared. With all of that, what we want to find out is how fast we launch the ball. That will be u, which means we don't need t at all. So our most relevant equation is v squared is equal to u squared plus 2as. For plugging it in and solving, you'll end up with an answer u is equal to about 86 meters per second squared. Very, very fast if you want that baseball to go all the way to the top of the Empire State Building, which makes sense. You will need to know these motion graphs. My recommendation is don't memorize all 21 of these graphs. Know the general themes, like constant displacement. Displacement is not moving. So the velocity is 0, acceleration is 0. For constant velocity, both positive and negative, you have a constant slope in your displacement with just a constant positive or negative velocity and a zero acceleration. For anything that is accelerating, you're going to have a curved displacement and then a constant slope on your velocity with a constant acceleration the entire time. We can use these graphs to tell us information about them. So if you have a displacement versus time graph, you take the slope of that and you'll end up with velocity time. If you take the slope of velocity time, you'll end up with acceleration versus time. And the easy way to remember that is if you look at the graph itself, displacement versus time will be something in meters and something in seconds. If you take the slope of a line there, you have rise over run, meters divided by seconds, and that gives you meters per second or velocity. If you go the other direction and we find the area under the curve of a velocity versus time or acceleration versus time, that will give you something else. So area under the curve of velocity versus time will give you the displacement, and we talked about that a few times as well. So thinking back to those 21 graphs, we can determine just the general shape of what will happen if you throw something up in the air, comes to a stop, and then comes back down. So let's start by saying my displacement, we're going to start not at 0. I'm going to go up, it slows down, and then makes it all the way down to the ground. My velocity starts with an initial velocity, and then there's a constant slope crossing the x-axis at the highest point. And then it turns back around and hits the ground, moving at a negative velocity. For acceleration, that's just the slope of our velocity versus time graph, and it is always exactly the same. That is always going to be a negative 9.81 meters per second squared. So then, it's important that you know how this turns into a two-dimensional type of motion. You might remember this graph or this diagram from when we talked about it before. If you have something moving in 2 dimensions, the horizontal is independent of the vertical. If you look at the horizontal component in every case here, it's always exactly the same. It's the vertical that's changing. The vertical starts pretty positive and then it decreases until it's 0, and then it starts increasing going down. If you take what's known as the resultant vector, this red vector, that is always the instantaneous velocity at that point, which is the direction that it is traveling. So if you are solving an XY type problem, a couple things that you need to know. You're going to start with y and pretend it's just free fall. If it's free fall, you know that acceleration is a negative 9.81 in the y direction. The air time is going to be the same for x and for y. So we know tx and ty are the same, which is why I typically draw it as 1 cell instead of 2. And then, once we have the time, we can move over to the x side. We know that the acceleration of x, there's nothing causing it to move faster or slower unless there's a lot of air resistance or there's some rocket pack or some thrust. Because of that, we can use the simple s is equal to vt, or v is equal to s over t, distance over time, to find both u and v, because u and v will always be exactly the same. If it's not speeding up or not slowing down, the velocity does not change. So for a horizontal projectile like this, there are some things that we know about this scenario. This is the classic spitball example where we know it's 1 meter to get to the wall and it goes down by 15 centimeters. So we can plug those values in to this chart. I apologize, this is in a different order than typically. It's, instead of SUVAT, it's UVSAT, but the process is still the same. That I'll plug it in here for S in the x direction is 1 meter. In the y direction, it goes down 15 centimeters. 15 centimeters is the same as 0.15. So we'll say negative 0.15 meters. showing that it goes down negative 15 centimeters. Acceleration for x is always going to be 0 meters per second squared. Acceleration for y is always going to be a negative 9.81 meters per second squared. And we know that initially there is no y component of that initial velocity. So we say u for y is going to be just 0 meters per second. With that in mind, I can start with the y and find what t is. Ultimately, what I'm looking for is what is the initial velocity u in the x direction. So that's my goal, to get there. Before I can get there, I need to find t. To do that, I'm going to use this equation. S is equal to ut plus 1/2 at squared. S is negative 0.15. U is 0, so that just cancels out. And I'm left with 1/2 times a negative 9.81 times t squared. Solving for t, I get time is 0.175 seconds. 0.175 seconds. Once I have that, I can use the time, the distance, to find my velocity. And again, those are going to be the same. So we can just think of it as, all right, this velocity, v, whether that's u or v, is equal to how far it goes divided by the time, distance over time, or 1 meter for every 0.175 seconds, to give you roughly 5.72 meters per second. And that is our final answer, 5.72, 5.72. That's how fast it exits the straw.